Oh, good afternoon. Sort of a rainy, pleasant Monday afternoon. And today we are going to discuss, this is our last, newest material for the semester, systems of equations and matrices. Let me go ahead and tell y'all what the heck a system of equations is. Okay. A system of equations system is singular, so I'm using the singular verb, is a collection of two or more equations. I'm defining system, not equations. An equation is a statement that has an equal sign. If you have a couple of two or more equations written together, that's called a system of equations. I may as well let you see one right now. If I click, oh wait, what is this? I told Tim, don't leave your stuff up there. Oh, can't believe he has all this stuff open. I hope there's no personal email, not personal, but a student email there. What the heck? There. Here's problem number one. See if y'all can see this. Just so I'm not ready to do the problem yet, but here's a system of equations. Notice it's just two equations. These equations are, would y'all say these equations are linear or quadratic? Are there any exponents up here? No? So what are y'all thinking? Linear or quadratic? Linear. So we have two linear equations. To solve a system of equations means to find the point of intersection. To solve a system of equations, means to find the point or points of intersection. I'm going to do this. I'm going to write point and then I'll put an S in parentheses. It might be points of intersection. Since that number one is a linear, both of them are linear equations, that means we have two lines. Let's think about if you were drawing two lines, how many points could two lines intersect in? The most common would be right here. Those 2 points intersect, those two lines, the red and green, are intersecting in exactly 1 point. That's the most common situation. If you were going to draw two lines, they intersect in 1 point. Would it be possible to draw two lines that intersected in 2 points? Say no. No, it would not be possible to draw two lines that intersected in exactly 2 points. What about are the lines that never intersect? What do you call those? Parallel lines. If we had parallel lines, then those have no points of intersection. They never intersect. I'll attempt to draw parallel lines, something like that. There's one. Let me see. Pretend they're parallel. I say pretend because if I kept drawing them out, they'd probably, of course, I can't eventually they'd intersect, okay? But that's only because my lines aren't truly lines, are they? They're just marks. I can tell that's sort of curved right there, okay? So parallel lines never intersect, so there's no points of intersection. Let me look at this problem number 1. Look at this, the way the instructions are worded. Okay, the solution is type an ordered pair. That would be if there's just one point of intersection. That's the most common case. Now, there's no solution. That would be for parallel lines. But what about this infinitely many solutions? There's a case I haven't drawn here. I drew 2 lines intersecting in one point. I drew 2 lines that never intersect. That would be no solution. There's one other possibility that people often overlook. They're called coincidental lines. And those are lines where one line is directly on top of the other line. One line is on top of the other line. One line is on top of the other line. So imagine if we had our red line and we drew a green line right on top of it. Just so it'll be easier to tell, I'm going to try to draw it where the green line is a little, well, they're the same size, but I'm trying to indicate. The green line is on top of the red line. With coincidental lines, there are infinitely many points of intersection. Every point of intersection. Many points of intersection. Okay, so that's why we have those. Okay, I'm thinking this doesn't look, this is blurry to me. Is it blurry to y'all? No. It's just my bad vision. I'm going to see about having surgery tomorrow if this specialist says that my eyes are bad enough to do it. I don't know whether I should be hoping he says, yes, your vision's bad enough to have this surgery, or that he says, no, your vision's okay. You don't have to have any surgery. Okay? So, I think I'm going to go ahead and tell you how, when we're going through solving these, and I haven't done one where we're solving them yet, but when you're solving, if you wind up with 0 on one side of your equation and a non-zero number, anything other than 0 on the other, then that means you have parallel lines and there's no solution. If when you're solving, and I'll illustrate this in a moment, when you're solving, if you wind up with 0 on one side and 0 on the other side, I should have said 0 on both sides, then there's infinitely many points of intersection. Okay? Now, we're going to see 2 methods for solving well, actually, we're going to see, before this whole thing is over, today we're going to see this week. And this assignment, we're going to see elimination, substitution, augmented matrices, and we're going to see 4 different ways of solving. Today we're going to see maybe 3 of them. Okay? But the ones that I'm first going to do, 2 methods to solve systems. Substitution is the first method, and elimination is the second. Okay? So we have elimination and substitution. Those are the first two methods we're going to see today. And I guess that was really stupid for me to say two methods. Well, we're going to see some more methods. You know what? I'm going to say just methods to solve systems of equations. Substitution and elimination. And let's do problem number 1 to illustrate substitution. Okay? And I'll talk you through. Here's problem number 1. It says solve the following system of equation by the substitution method. So let me write it down. 9x plus 8y equals negative 37, and x equals 4 minus 6y. X equals 4. Ooh, can y'all? Oh, wait, well, you know what? 4 minus 9y. I think I said 6y, didn't I? But it's minus 9y. So 9x plus 8y equals negative 37. X equals 4 minus 9 or y. And we're doing this with substitution. Now, if at any time when I'm working this problem out, illustrating, showing you how to do substitution, if at any time I get a 0 on one side, oops, I thought I'd already flipped, and a non-zero number on the other, we can stop and say, choose the option no solution. If on the other hand, if at any time we get 0 on both sides, we can stop and say infinitely many solutions. So here's problem number 1 using the substitution method. What we have right here are two equations with two different variables, x and y. In order to solve an equation, we ultimately want x equals some number, or y equals some number, okay, whatever the variable is. Well, what we're going to do is go from, I'm putting a little brace mark here to indicate there's two equations. We want to write just one equation. We have two equations with two different variables. We want it with just one equation. With the substitution method, you have to have one of the variables isolated. We have that. And now plug in or substitute into the other. I have x equals, I hope this mess up that I wrote right here isn't bothering you. X equals 4 minus 9y. Let's plug that into the other equation. It's going to look a little messy, but the reason we're doing this is we're trying to get just one equation out of both of these. Instead of two equations with two variables, we want one equation with just one variable. Okay, so I'm going to take this x equals, and in place of that x, I'm going to put 4 minus 9y. And you might think, well, this looks worse than the other one. No, it isn't. Why am I saying it's not worse than what we started off with? Here we have two equations and two variables. Now I have just one equation, and the only variable we have is y. What kind of equation is this? Linear or quadratic? Linear, because there's no squares. Remember, for a quadratic, it has to be square. If you have no exponents, then it's just a linear equation. So to solve this linear equation, I'm going to distribute the 9. So what would we have? A 36 minus 81y. And we still have the plus 8y. And the equals negative 37. is this an equation that we know how to solve? Could we get the y by itself? Oh yeah, but first let's combine the two y's. That negative 8y plus, negative 81y plus 8y. I have 36, and the minus, what's negative 81 plus 8? It's a negative 73. Y. And now just go through and get that y by itself. Oh, let's see. I guess here's what I'm going to do. To get the y by itself, I'm going to subtract 36. So 36's are gone, and we have a negative 73y on the left. And what are we getting on the right? Negative 37 minus 36. Is that another negative 73? I think this one's rigged nicely so you don't get fractions. Okay? Now what's the only thing I need to do now to get the y by itself and have y equal a number? Divide both sides by negative 73. And we get y equals, is that 1? Now notice, at no time, if everything had just started subtracting out and we'd gotten 0 over here on the left and 0 on the right, then we would have said infinitely many solutions. If on the other hand, everything subtracted out and we had 0 on one side and a non-zero number on the other, we would have said no solution. But, what we have, looking at the way the answer, what it says is, it's not no solution or infinitely many. Our answer should be an ordered pair. Okay? With just one solution. If you just have one point of intersection, your answer should be an ordered pair. That means you need a value for x and a value for y. What we just found is our y value. How the heck are we going to find x? See, our answer is an ordered pair. We just found the y coordinate. And I should have written it in the blue, but I didn't. Okay? How are we going to find the x? Have any idea? I'll give you a hint. The name of this method is substitution. Do you think maybe it has something to do with substituting?
Substitute the y.
Yeah. Take this number 1 and plug it into either, go back to the original problems, plug it into either one of the equations. Generally, the one where the variable is by itself is the easiest one to use. So, I'm going to take the y and plug it in right there. So we have x equals 4 minus 9. And in place of the y, I'm going to put a 1. Now be careful. Multiply before you subtract. The 9 minus 1 is 9. Although I guess on this rare problem, Tim, look at that. If they didn't do the order of operations, they could have gotten...
they would have still gotten
you would have
the right answer. Wow.
Negative 5. They're very quiet, Tim.
What did you do to them?
I don't know. So there's our ordered pair. Negative 5, comma 1.
Those two lines intersect at the single ordered pair negative 5, 1.
That's the only point that intersect that. Okay? So, Tim, do you want to type that in?
Oh, yeah. Okay.
We've already discussed the two other options of it, why it's not infinitely many and why there's no solution. What's not no solution? Okay. If at any time you get 0 equals 0 or 0 equals, if all the variables can, subtract out. So let's try to summarize what we do. With substitution, you've got to have one of the variables solved, one of the variables isolated. Then you plug that into the other equation. So here's what we do. Isolate one of the variables. Hopefully, or like on number 1, that was already done for you. Then substitute that into the other equation. Well, that was problem 1, and one of the variables was already isolated. The natural question to ask is, well, what if they're not? What if they were both written in this general form here, like the first equation, ax plus by equals c? What if this had been x plus 9y equals 4? Well, then you're going to have to isolate one of those variables. As a general rule of thumb,
where's the problem?
You got it. You had like 1,001 tabs opened all of a sudden. Your email was open, and I had to. No, I think it might have already. Okay, let's look at number 2 here.
Number 2.
You just flipped it.
Mm-hmm.
On number 2, the variables. There's not one already isolated for us, is there? So let me write it down, and then we'll discuss how we're going to do it. It still says solve using the substitution method. So problem 2, 2x plus y equals 12. And 3x minus 2y equals 4. 3x minus 2y equals 4. And I'm going to put little braces around here just to indicate. There's the two problems. Our goal is to write just one problem. Okay, one equation. If you're going to use substitution, you must have one of those variables isolated. Here, the red X was already isolated.
Okay, look at number 2. There's one variable that would be the easiest to solve. You want to, if you're going to have to isolate a variable, you want to try to isolate one so you don't pick up fractions. There's one that you could isolate and not pick up any fractions. Which variable in which equation?
The red X, the red X, the black X, the black Y, or the red Y. Which one would be the easiest one to isolate? The black?
No.
If you isolate it, you're going to wind up having to do what? To divide by 2? You don't want to get a fraction, but you're half right. The black? Y.
Choose the one if there's one that only has a 1 or a -1 coefficient. That's the one you want. The one that doesn't have a number sitting there in front of the variable.
I think I'm going to isolate this Y. What would I need to do to get the Y by itself? I would need to move that 2x.
That's right.
So
she said subtract 2x.
Okay. Mm-hmm. So I'm trying to decide, do I want to write 12 minus 2x, or would y'all rather me write negative 2x plus 12?
I like 12 minus 2x.
Oh, okay. But just don't get carried away and get a 10 there, okay? So we've isolated one of the variables. Why did we not isolate the black X? Theoretically, that's fine. You could do that. and you would get the same answer.
Eventually.
It's just going to, if you had isolated the black X,
you'd have to move the Y over.
And then what would you have to do to get the Y by itself? Oops, to get the X by itself. That's an X. Oh, wow, I'm messing up today.
You'd have to divide by 2. You'd have that big fraction to substitute in.
And it's always easier if you're not having to plug a fraction in. Okay? So we've isolated one of the variables. Now plug that into the other equation. So in the other equation, in place of the Y, that red Y, I'm going to put the 12 minus 2x. So let me write that 3x minus 2 in place of the Y. I'm going to write 12 minus 2x. And how would y'all go about this? I guess we would
distribute the -2 to get. Okay.
Yep.
Good.
That's right. Now let's combine the like terms because there's two different x's. There's a 3x and a 4x. I could write that as 7x.
What are we going to have to do to get that minus 24 over to the other side? What are we going to have to do?
Isolating the x. Yep.
Add 24 to give us 7x equals.
Oh, I'm hoping we don't get a fraction here.
28. No.
I know.
And look at that. Isn't my lab nice to us? What are we about to get for x? 4. I was thinking we might get a fraction on this one. Fortunately, we didn't. But you could get a fractional value, but then you have to substitute in that fraction to get the other value. Here it's just a 4. That means that these lines are going to intersect at a point where the x coordinate is 4. Go ahead and write the order, half of the ordered pair right there.
The x coordinate is 4. That's going to be our answer. How do we find the y coordinate? Well, actually you have 3 different equations you could use here. You could plug it in here, a 4, and figure out y. Or you could use here, or heck, what about this one right here? The y is already by itself. If I plug the 4 in right there, is that going to give me y equals pretty easily? What would I have? Is anyone following what I'm doing? Hey, are we getting 4 again? Well, it won't always work like that. And on this one, why did I write the x in black? I should have written it in red. I'll just say x and y. Okay. And this is called substitution, but there's a lot of problems with this substitution method. One of the big problems is what happens if you couldn't isolate one of the variables without getting fraction. Suppose there'd been a number in front of that y right there, like a 5 or something. If you can imagine if you had a messy fraction plugging it in, that's going to be a little messy. Did you type that answer in and get it right? But so fortunately for us, we have a lot of work. Make sure you put the parentheses there, okay? I don't have them included. If you don't type the parentheses on the homework, I think it'll say you left off the parentheses or something like that. Your answer's an ordered pair. It should be an ordered pair. You need to type an ordered pair. But if you do it on a test, it's just going to count it wrong, okay? So make sure you're writing it as an ordered pair, okay?
Now, the second method, elimination.
Let's see, so that was substitution.
I think we're ready for elimination. With elimination, you need to have your like variables aligned. Notice that's what we have here. The x's are aligned, the y's are lined up. On the other side, you need to have your constant terms. So that's called standard form for a linear equation. You need it in standard form. The x's lined up, the y's lined up, the things without variables on the other side of the equal sign.
With elimination, we're going to just add vertically in such a way that one of the variables is eliminated. If I drew an equal sign right here and just added vertically, which variable would we lose? Which variable would subtract out?
Oh, that we can't see.
Oh,
right?
10.
Thanks. I was wondering,
Oh.
what is Zelda pointing at? Okay. And it still didn't dawn on me. My mind's elsewhere.
Oh, Tim, I hate that you've
Here's
recorded
something
that
you're
your
going to need
mind
to
is
remember.
elsewhere to incline.
You need the same coefficient but opposite signs. That's the trick. Notice the coefficient for x in the first equation is a positive 1. What's the coefficient for x in that second equation? Move your pen so they can see it. What's that coefficient? In the first one, it's a positive 1. What's the second one? A negative 1. You need the same coefficient but opposite signs. Because then start adding those things together. 1x plus negative 1x, you've eliminated the x's. Well, add the y terms. What are we going to get? 10y equals...
I'm thinking 40. Am I
40?
Is it 40? Yours is 50 on your your thing, okay? And now, do we have an equation we can solve? Remember, our goal is to get x equals a number and y equals a number. Can we get y equals a number here pretty easily? By doing what? What do we have to do to isolate the y? They're just not talking. Divide by 10. And we get y equals 4. Oh, wow, Tim. So if in doubt, just guess 4 for everything. Okay,
so that means if you drew a picture of these two lines, they would intersect at a point where the y coordinate is 4. Now, most people don't do pure elimination. What they do is a combination of elimination and substitution, and that's what I recommend you do here. We eliminated to find y. If we were going to continue using elimination, we'd have to start all over. We'd have to try to eliminate y's by changing their coefficients, but we don't have to do that. We know substitution. We can substitute in. We know that the y value is 4. It doesn't matter which equation you use. Substitute that y value of 4 into one of those equations. Let me ask you all this. Which equation do you like better? The first one or the second one?
They don't like either of them. Which one would be easier to plug into? Generally, when I look at this stuff, choose the one with fewer negatives.
So with that in mind, smaller numbers and fewer negatives,
okay,
I'd use the first one. You'd get the same thing if you plugged the 4 into the y on the second equation, but I think it's easier arithmetic if you substitute into the first one.
Is it clear what I'm doing right now? I'm plugging the y value that we found into, and I'm using the first equation. Okay. So we have x plus that 3 times 4, is that going to be a 12? It's 14. What would we do then? Subtract the 12. So x equals, say it again. 2.
So now we know if we were to graph these lines, they would intersect at the ordered pair 2, 4. With elimination, you need the like variables aligned, and you need the same coefficient but with opposite signs.
Let me see. Okay.
So
Type that in, and I'm going to write what you just said. Hey, I was going to say, type it in without the parentheses just to see what it's going to do. But that's
I'll do that the next time.
Let me write what he just said. With elimination, you need the like variables aligned. You don't want an x over a y. Like variables. I'm going to say lined up.
Lined up, okay.
You also need one of the variables to have the same coefficients but with opposite signs.
Like in problem 3, x had a positive 1 and a negative 1. And you say, well, suppose you don't have that. Well, you're going to have to make it. You're going to have to make it have those same coefficients, but opposite signs.
Opposite signs. Okay. Let's see.
I bet you this problem number 4 isn't going to have the thing just set up for you so painlessly.
I bet you're wrong.
Oh, I guess you're right.
Okay.
You're right. I was wrong.
Let's see.
What about 5?
Well,
there's one. Number 5. Okay. This one here.
3x plus 8y equals 5. And 2x minus 8y is equal to negative 10. Okay, with elimination, you need the like variables lined up. They are, right? X's are lined up and the Y's are lined up. You also need one of the variables to have the same coefficient but opposite sign. Well, the X's, no, those are different coefficients, 3 and 2. But look at the Y's.
Tailor-made for elimination. We're ready to add the two equations together.
So we will. That's my equal line. I'm adding vertically, and I'm going to have what, a 5x.
3x and a positive 2x. 3 plus 2 becomes 5. What's about to happen to the y's? Okay. Equals. What are we going to have on the right side?
5, yeah. 5. Is it positive or negative? Negative. Okay. Okay, this one we can solve without too much trouble now. Divide both sides by 5 to get the x by itself. And we're getting x equals what? -1.
So these lines, if you drew their graphs, they would intersect at an ordered pair whose x-coordinate is -1.
Now, how are we going to find the y-coordinate?
Once you know one of the values, what do you do to find the other one? Plug it in, substitute it in, and I'd use the thing that has fewer negatives.
That's just,
That's just my own personal preference.
so I think I'll plug it into the blue one, the first equation, 3 times x plus 8y equals 5. So I'm putting a -1 in place of the x. Now, if you'd used the red one, you're going to get the same answer. Let's see, the 3 times -1, that's -3 plus 8y equals 5. So, is that one we can solve it pretty easily? How would I get the y by itself? Would y'all...
There's only one correct next step. What is it?
Yeah,
Add 3 to give us 8y equals 8, okay. And then divide by 8 to give us y equals, okay. So if you drew those lines, they would intersect at the ordered pair, -1, comma, +1. That's what we mean by the same coefficient but opposite sign. Okay, let's type in that answer. And let's see what happens if I just type -1, comma 1. If I don't type the ordered pair. No, they don't say that you don't use parentheses. They just tell you it's wrong. So, you gotta put it in parentheses.
Now, at this point, you can check these answers without too much trouble just by plugging in. If we took -1, comma 1 and plugged -1 in for x and +1 for y, we should be getting 5 on the first one and -10 on the second one. 3 times -1 is -3. 8 times 1 is 5.
No, it's
It's 8. So -3 plus 8, that's sure 5. So it checks in the first one. It should also check down here. 2. Oh, Tim, I'm here pointing and stuff, and they don't see it. I'm plugging these numbers into both equations. I should get a 5 on the first one. Not down here, I should get a -10. 2 times -1, that'd be -2. -8 times +1 would be -8. So -2 minus 8, that gives me -10. Okay. Any questions there?
But looking at number 5, they tell us to use elimination. When I'm solving a system of equations, elimination is my preferred method.
You want to do that one?
I prefer elimination more than substitution, okay? And so, let's see there. Let's write down number 5. We have 5x plus 3y equals a -11. And 3x minus y is equal to -1. Let me make sure. 5x plus 3y. Yep, okay. Switch. We need like coefficients, but with opposite signs. Well, 5 and 3, there's nothing like, we don't have like coefficients. We don't have opposite signs either. Look at the y. We have a coefficient of 3. What's that coefficient down here in the green equation? I don't see a number there. -1. So it's not the same number, but it's
like
not.
that one in pink, -1.
Okay. They're not the same number, but at least they have opposite signs. I think I'm going to try to eliminate y. I need to change that one y that I'm pointing at there to a 3. Remember that you can multiply both sides of an equation by any non-zero number you want to and not change the equality. So what I can do, I'm going to multiply the second equation by a 3. The first equation is going to stay as it is. There's no arrow. It's a 5x. The first equation will stay 5x plus 3y equals -11. The second equation, though, we're multiplying by 3. 3 times 3x will give me a 9x. I'm distributing the 3 there, there, and there. That'll give me a minus 3y. What am I going to have on the right-hand side, right here? -3. -1 times 3 gave me a -3.
Like that student said so many years ago, 33 years ago, Tim, you're just making
I'm just making it
work.
work. I'm making it have this like coefficient but opposite signs.
And I'm going to say the most basic problem-solving strategy, if you know how to do problem 4, you come to problem 5 and don't know how to do it, make it look like number 4. And that's what you just did.
Yeah, you're right about that. Let's add the two equations together. We have a positive 5x plus 9x. That's a 14x. What's about to happen to the y terms when we add those? So we've eliminated the y's. -11 plus a -3. This is working out real nice. -11 minus 3, isn't that a -14? What do I do to solve for x here? Divide by 14 to give me x equals -14 divided by positive 14 is a -1. That means that these two lines are going to intersect at an ordered pair where the x-coordinate is the x-coordinate. I found x. X is equal to -1. What do I have to do to solve for y? I need to know the y value now. What will I do? Okay, I'm going to plug in the -1 and I'm going to choose the equation that has the fewest negatives. I'm going to use that blue one right there. Now I'm going to use 5x plus 3y equals a -11. I'm going to plug in that -1 for x. So we have 5. Replace the x with -1. 5 times -1 is a -5 plus 3y equals -11. I'm trying to solve for y. What do you think I'll do next? Add 5 to give me positive 3y equals, it's -11 plus 5 will give me a -6, and then divide by 3, good, to give me y equals -2. Am I talking louder, or is the microphone set louder? It just seems like I'm echoing.
You're echoing because it's so empty.
Oh,
in
that's
here.
it. You're right. Okay.
Something happened this past weekend.
Where did the rest of the people go?
I got a drop.
Oh.
Yes, someone dropped the class. Well, my class, anyway.
Okay, an ordered pair of -1, -2. So if you're trying to use elimination and you don't have like coefficients, you may have to multiply both of the equations.
We'll see some really nice applications, but could you do this one just to illustrate? We did one.
Okay,
Here's one that we're making up. I just want to illustrate what I mean by that 0 equals 0 or 0 equals non-zero. But we'll see some really nice applications on Wednesday. And we'll use probably use elimination. Elimination is my favorite method.
After teaching Math 1324 for so many years, I prefer elimination.
Yeah.
Yeah. Okay, let's suppose we had this problem.
Chance to write it down.
Okay.
Suppose this is one that said solve by elimination. This is just an example that made up. I just want to show you what I mean when I say about the 0 equals 0 or 0 equals non-zero. This particular problem is tailor-made for elimination.
Notice we have the same coefficient but opposite signs on x. We also have the same coefficient with opposite signs on y. So this is pretty good. 9x minus 9x, that gives me 0x. What are we going to get here? 0 plus 0. So we have 0 on the left side. Everything canceled out. What have we got on the right side? Negative 36 plus 86 gives me a positive 50.
Notice how there's no variables. You're not going to get x equals a number or y equals a number.
Here, as soon as we'd gone through this first part, adding them together, we were able to say these lines intersect when x is equal to -1. Now, these lines intersect when 0 is equal to 50. Is 0 ever equal to 50? No, 0 never equals 50. 0 never equals 50, so these lines never intersect. Did y'all follow our logic? 0 never equals 50. So these lines never intersect. What do you call lines that never intersect? Parallel. These lines are parallel.
The answer choice that you would choose is the no solution. See, they'll give you that. Now, suppose
that had been a 36 down here. Suppose it had said 0 equals 0. Well, how often does 0 equal 0? Always. That means the lines always intersect. If you had 0 equals 0, that means you have one line sitting on top of another line. Okay, there. If you wind up with 0 equals 0, coincidental lines, infinitely many solutions, because every point is common.
I put a dash and then I tried to change it to a colon.
It looks like something. It looks like a little wrench
and my
to me.
S doesn't look like an S. It looks like a 5. This is horrible.
Oh, Tony. Okay. Any questions there? Now we're going to start talking about matrices.
It's just this last assignment just has a lot of elimination, substitution, a little bit of matrices. But we're going to spread it out over 2 days. Why? Because we have the 2 days. And I've already told them that makeup in classes on next week.
Okay. A matrix is just a rectangular arrangement of numbers. Nothing special about it, just a rectangular arrangement of numbers. And the plural of matrix is matrices. I didn't care for that movie Matrix from, when was it, late 90s? I didn't care for it, but the sequel should have been called Matrices rather than Matrix 2 or something, don't you think? Like Alien and then Aliens. I thought that was so clever back in the day.
Way before they were born.
Oh, you always have to bring stuff up like that, don't you? Okay. Oh, goodness.
I just wonder if your college teacher had been talking about stuff before he was born.
Before I was born?
Before you, as a student, were born, it would have been going in one ear, out the other. Just like years ago, first year here, I was talking about I had a good class to this coworker, and he began talking, he remembers when he had a good class, and I was there listening to him, and then he talked about, but the Vietnam War was going on, and everyone wanted to make A's then. I turned off. Wait a minute. I'm talking about today, and he's talking about the Vietnam War. Okay.
Okay. Stop it. We're getting distracted. We need to get through this stuff, okay? We generally enclose a matrix using rectangular brackets. It looks like that closed circle interval notation stuff, doesn't it? Here's an example of a matrix. Here's an example of a matrix. The horizontal arrangements are called rows. So this is row 1 and row 2. The vertical alignments we refer to as columns. So this is column 1, column 2, and column 3. The size of a matrix is identified using the number of rows and the number of columns, just like the size of a rectangle. Let's say you have a rectangular living room and you're buying, does anyone have carpet anymore? Well, suppose someone's buying carpet and they're measuring the size. You don't just go into the carpet store and the flooring store and say, I have a living room and its size is 10. No, you give the dimensions, the length by width, or the height times, the base times height, whatever. For the size of a matrix, you give it based on, where did you get that pink pen, Tony? It's the number of rows by the number of columns.
Notice how you called that X is by, just like you would if you were talking about the dimensions of a room, 12 by 15 or something.
So this matrix there were 2 rows and there were 3 columns. So that is a 2 by 3 matrix. That's not the same thing as a 3 by 2 matrix. A 3 by 2 matrix would look something like this. 3 rows and only 2 columns. This would be an example of a 3 by 2 matrix. You can refer to any spot on the matrix based on the row number and the column number. If I wanted to refer to this, let's say right there, that position, that's row 3, column 2. In row 3, column 2, we have the number 1/7. In a little bit, we're going to be finding determinants. Determinants are unique numbers that are assigned to a square matrix.
What is a square
What
matrix?
is a square matrix? That's a good question, Tony. You're always asking those good questions. Well, we know, if you think back to geometry, you would have learned that a square is just a rectangle where the dimensions are equal. The base and the height are the same. So what do you think we're going to say about a square matrix? What's the connection between the number of rows and number of columns for a square matrix?
I'll give you a hint. These are not square.
These two, that's not a square matrix. This thing here is not a square matrix. To be a square matrix, what do you think would have to be true about the dimensions? Same
Yes.
number. Okay,
Right.
so the number of rows is equal to the number of columns. We can use matrices to summarize the coefficients and constant terms from a linear system of equations. Everything we're doing today and Wednesday, will ultimately go back to this idea of systems of equations. And we can use matrices to summarize. We can use matrices to summarize the coefficients and constants of a linear system. But to do that, it needs to be like the systems when we were solving by elimination. You need like variables aligned on the left side. You need to have the constant terms on the right side. And in all this time, a matrix that summarizes the coefficients only. If it's just summarizing the coefficients in a linear system, that's called a coefficient matrix. A matrix that summarizes the coefficients and the constants is called an augmented matrix. Let me write that down. An augmented matrix.
Now I'm going to give the pep talk. It's sounding harder than it is. Just
An augmented matrix summarizes both the coefficients and constants in a linear system of equations. I'll just say in a linear system. What we have to do in this class is set up augmented matrices and interpret augmented matrices. So,
let's look at number 6. I hope we haven't been typed up.
write an augmented matrix for the following system of equations. Let me write out this problem. This is number 6.
I tried to make it a little bigger.
Negative 9x plus 2y equals 5. And 5x minus 4y equals 9.
Hey, if we were actually told solve with elimination, how many of y'all would multiply the first equation by 2? Would that do it with elimination? But we're not doing elimination, but
If we were, that's one of the things. That's one thing. If they say solve by elimination and you're like, oh, I'm going to solve it by substitution, you'd still get the same answer. Okay?
I'm more apt if it says solve by substitution
I
to
use elimination too.
But not when I'm teaching it.
I'm going to do what the instructions say usually
When you're
when I'm teaching. Okay, you need to make sure the like variables, there are my x's, they're aligned. Here's my y variable aligned, and my constants are on the right-hand side. There are two equations. That means my matrix is going to need my augmented matrix will need two rows. The first row is going to summarize the coefficients of the x variable. Those numbers are negative. The first column, pardon me, are going to summarize the coefficients of the x variables, -9 and +5. The second column will summarize the coefficients of y. Well, that's 2 and -4. When making an augmented matrix, to indicate that you're moving to the other side of the equal sign, you draw a vertical bar. This vertical bar is taking the place of the equal sign.
Equals right up here.
Oh, I like that. Okay, there, equals. And then my column of constants, 5 and 9.
I can't believe you've talked for 15 minutes to show them how to do this problem.
I know it. That hasn't been 15 minutes.
Well, okay.
10 minutes.
10 minutes, still. Let me go ahead.
I could have just gone to said next problem. Okay, do this, because look at what we're about to do.
Right, couldn't we have just said, okay, next problem. Type the numbers in, -9, 2, 5. There's the first equation. 5, -4, and 9. There's the second. I tried to make it bigger, but okay. That's called an augmented matrix. Okay.
Let's go to the next one. Write an augmented matrix for the following system of equations. Let me ask you something. Look at that problem. Look, there are 3 equations. That means we're going to need how many rows in our matrix? There are 3 equations, so we're going to need 3 rows. How many variables are there? There's 3 variables, x, y, and z. So Tony, are you pointing there? I don't think I have to write out anything. They've got the matrix set there for us. I think, and look at how they already have the like variables aligned. They have the constants by themselves on the other side. I think they could just call out those answers to you.
I'm going to go I'm going to go horizontally because I'm going to be hitting tab, and it moves across.
So 5. What's going in the next square?
Oh, it didn't move when I hit 5. Okay. 5.
I heard -4.
Oh, okay.
Next. 2. Next. And the second row. What goes in that box? Oh, okay. 5 again. Next. Okay. Well, I'm assuming that y'all are just quiet.
Oh.
Now, the third equation. What's going to go in that first box? 0. There is no x there, so that's like 0 times x. If a variable is missing, you assume a coefficient is 0.
And you got to put a number. Matrices have numbers.
Notice matrices don't have variables. You don't write the x. You don't write the y. That's why matrices are used so much for computer programming, because it's all numeric. And the last box, we have a -9. Just for the record, they don't ask us, but what size matrix is that? How many rows do we have? 3, okay. How many columns do we have? 4. That's a 3 by 4 augmented matrix.
Now that you mention it, they used to ask that.
I know they did.
I'm wondering why they don't now. Huh.
I know.
Okay.
They don't even ask for the size. That's why I talked about the size. I thought they were going to ask us.
Oh.
Now we've got to go backwards.
In math, algebra especially, you do it one way, then you do it in reverse.
Okay,
You want to write it down or just type it out?
I think we have time. I'm going to write it out. Give me a moment. I have the matrix 1, 0, 5. The second column is 9, 4, 0. The third column is -4, -1, 8. We move to the other side of the vertical bar. 7, -4. Is that an 8 also?
9.
Oh, a 9. Okay. And switch over to my paper. There are 3 rows. That means we need 3 equations. Look to the left of that vertical bar. There are 3 columns. That means we need 3 variables. I'll use X, Y, and Z because I think that's what they're using in the answers. And I'll put a little equal right there above that vertical bar. Let's see the first row. That says 1x, and that's a positive 9, so that's a plus 9y. What am I going to do with this minus 4? What am I going to write? No.
Oh, you're right.
Minus 4z that equals here 7. Now the second row, 0x, what is that saying? Are we going to have an x here for the second equation? No, there's no x. There's a positive 4y. What else? Minus 1z equals -4. Okay, there's the second equation. Y'all call out the third equation. 5x.
No y.
No y, so we have 5x plus 8z. That's a positive 8, so it's a plus 8z equals 9.
Notice how you wrote the
I wrote the like terms lined up. Are they going to do that over here?
You see
No,
the
they
X,
don't. Oh, I don't like that.
Okay, so this is a 9. And, oh, look, be careful. They've already put the minus.
Oh,
all you type
I
is
would
the
have typed a
4.
-4. Do y'all see that? Look at that first row. We had that -4, and they've already typed the minus there. So all you're typing in there is a 4. So then we have a 4, and they already have the minus z. What's going to go in that box there? -4.
And a 5x.
5x. And an 8y.
8z.
8z, I mean.
And a 9.
In linear algebra, we perform something called elementary row operations, which takes a matrix like this, okay, one with all these messy numbers. Look at number 9, or is it number 10? Switch over. Is it
I think
number?
it's the
What's
next
it?
one, number
Okay,
9.
there. Look at what they've done. We have ones down the diagonal, starting the upper left-hand corner. We have ones down the diagonal. We have zeros above those ones. Let's write this down. In linear algebra, heck, in Math 1324, we learn a way of taking messy-looking matrices like number 8 and make them look like number 9.
Well, why would we want them with ones down that diagonal and zeros everywhere else?
Let's just write out the equation, and they tell us what letters to use.
X, Y,
Let's
Z.
switch over to my paper. They're telling us to use the variables X, Y, and Z. X, Y, and Z. Why in Math 1324 in differential equations we take matrices that look like this, and we perform a series of elementary row operations that aren't that elementary.
Did you
Until
say
we
Math
get-
1324 differential equations?
Or differential
okay.
equations. I can't remember the number for differential equations.
320.
2320. So Math 1324 or Math
Math for
13.
business.
Yeah. We take matrices that look like number 8 and we get them with ones down the diagonal and zeros above and below those ones. Why is that desirable? What is this first row saying? Okay, the 0y and 0z, you don't have a y or a z in the first row. You have 1x. That first row says 1x is equal to 6. Now in the second row, we don't have an x and we don't have a z. What's that second row saying? Y equals 8. And the third row, we have 0x plus 0y plus 1z equals 9. If we could take the matrix that looks like this and get it with these ones down the diagonal, these numbers over and zeros above and below, these numbers to the right-hand side are the solution to this system if there's a unique solution. That's why something like this is called reduced row echelon form.
And a calculator like this has a matrix key.
You could type in a matrix and then tell it to do the reduced row echelon form. I think it's RREF, the key, and it would get it in this form that we have here. And that means these numbers over here are the solutions to the system. Now, we're not going to have to go through and do that row reduction. We're going to see another way of solving systems of equations using matrices, but hopefully you see that having a matrix look like this with the ones down the diagonal, zeros above and below it, that's a big deal because now we know the solution to the system.
But there's a way to go with a calculator like this where you punch in the numbers for number 8 and then you hit another button and it'll do this for you.
It'll convert it to a matrix, and that is in reduced row echelon form.
If we had more time this semester, we might spend some time doing that, or we might go back and do more with logarithms.
Oh, well, yeah, I'd like that better. Okay.
But we're doing what we have to do.
Okay. Any questions there?
I don't even know, did I type in the answer on number 9? No, I didn't. Is it a hard one or not? What am I going to do? I'm going to type x equals 6, y equals 8.
If you wrote 1z, would they count it wrong? No, because they say simplify. They would not count it right. I think they would try
Have
it
you
and
looked
see.
at your number? Oh, okay. What the heck? 1z. Do y'all think it's going to count it wrong?
No, they gave it right. I'm surprised by that.
I'm curious, does everyone say X, Y, Z? Does everyone just type X, Y, and Z here for the answer on your number 9? Is that all you do? Or do they change the letters?
Say similar question.
Oh, okay, let me see. Similar question. Still X, Y, and Z. Is everyone's number 9? All you do, just remember on number 9, you type in X, Y, and Z.
See.
Oh.
Any questions there?
Are we ready to discuss determinants? Hey, notice, these were not square matrices. We had 3 rows and 4 columns. We're finally ready to look at a square matrix. This one's 2 by 2. Number 11 is 3 rows, 3 columns. But we're looking at something called determinants. And
there. A determinant is a unique number that's assigned to a square matrix. It's a unique number assigned to a square matrix.
Okay. We'll start off with the 2 by 2 determinant. 2 a 2 by 2 determinant, that means we have 2 rows and 2 columns. We're only going to show you how to do it for 2 by 2 and 3 by 3. If you're in a physics class, well, I can't imagine a physics class needing 4 by 4. No, I remember talking to Dr. Jonka about that years ago.
Yeah,
I'm assuming it's still the case that they only need 2 by 2 and 3 by 3.
changed.
Yeah, it hasn't. Okay. Even though Dr. Jonka's gone. Okay. To denote a determinant, we use what look like big absolute value bars. Notice there's no little hooks up there. It's not like these things with the little hook on top. You see what I'm saying? A determinant is represented using big absolute value bars. If you have to take a linear algebra course, you're going to see that properties of determinants are amazingly similar to properties of absolute value. Things like triangle inequalities that apply for absolute values apply for determinants also. But that's beside the point. To find a 2 by 2 determinant, it's the difference in the cross products. You multiply A times D minus, the formula has a minus, B times C. A 2 by 2 determinant has to be the easiest thing we've done this semester. It's just
I think the augmented matrices beat it.
Oh, okay. Well, I'll agree with you there. A 2 by 2 determinant is just the difference of their cross products when you start in the upper left-hand corner. So let's see. Let's look at the next problem. This is number 10. We want to find the determinant. It's a 2 by 2. -4, -4, and -5, 9. That equals, and remember the formula has that minus sign, that pink minus sign. Oh, wait. Okay.
Now, I don't mean for you to memorize A times D minus B times C. What you have to know to do these is the pattern.
You multiply -4 times 9, that gives me a -36. Minus, now you multiply -5 times -4, that's a 20. So that's -36 minus 20, -36 minus 20, that's a -56. I don't need another line there. There's my answer. The determinant for that matrix is -56.
Make sure, a lot of times students will get the wrong answer, the wrong sign, and what's happening is you're going the wrong direction.
They're doing BC minus AD. You always start, for determinants, you always start in the upper left-hand corner.
I say start with the first number. What's the first number in here?
That number there, you multiply minus multiply.
Yeah, start with the first number. Don't start over here or down here, okay? -4 times 9. Did I punch that in?
-36. And then the minus is from the formula. -5 times -4 is a positive 20. -36 minus 20, that's how I got the -56.
-56.
Next, is there another 2 by 2?
I don't think so.
Oh, this is a 3 by 3.
If we want to do another 2 by 2, I'll click similar problem.
Do y'all want to see another 2 by 2? Or it's just one
I think
enough?
they do.
I think they do
Yeah.
also.
Okay, look at this.
They're going to be so quiet.
Zelda's laughing. I can see the eagerness in their eyes.
wanting to do another one.
3, -1, and then -1, 9. Okay. Oh, there's the minus. I start off. 3 times 9 is 27. A minus from the formula. -1 times -1 gives me a 27 minus 1 gives me a determinant of 26. 2 by 2s are pretty painless. 2 by 2 determinants are pretty painless.
Unlike 3 by 3.
Let's see if they can see
So
it.
we're going to show you how to do the 3 by 3.
I'm going to show them the formula. I'm going to show them the formula.
If you need a 4 by 4 in another class, punch
comments?
it into your calculator. It's the enter on a calculator. You go matrix. Oh, gotta turn it on. And then once you get the numbers in there and stuff,
Is it in a DET function?
yeah, DET. You got to go to math. DET. There it is for determinant. Okay.
Here's a 3 by 3 determinant.
Okay.
Here's the formula for a 3 by 3 determinant. Okay.
3 by 3 has how many numbers in it? 9? Is that what I heard? Yeah, 9
total. There are 3 rows, 3 columns. So here we go. Okay. Now I'm just using A, B, C, D, E, F,
Is that E2.7?
G, H, I. No, that E is not representing the natural exponential. It's just representing an arbitrary
Is that I
real
an
number.
imaginary number?
I is not an imaginary number. It's just letters representing arbitrary numbers, arbitrary real numbers. So, let's see if y'all see. Let's see. Here we go.
Wait, I would start writing it out here.
Okay, right down here. Here we go. Left parentheses.
A, E, I.
It's A times E times I plus B times F times G plus C times D times H. Close the parentheses. Minus. Open the parentheses. Then C times E times G plus A times F times H plus B times D times I. There's the formula that you need.
This is not a formula that you just plug into. This
No.
isn't like the quadratic formula.
No,
You don't
this-
go plugging in the letters or something. Do y'all see the pattern? Surely you
There's
did
a
for the
pattern.
first one.
It's not a formula I memorized. I was looking down at what I was writing. I was looking at the matrix as I was writing out those letters. So there's some sort of a pattern. Does anyone see it?
Copy.
Here's my hint to you. Recopy the first 2 columns.
Then I
The
bet
first
you see
2 columns, write A, I'm going to write in a different color, A, D, G, and B, E, H.
Now do y'all see the pattern?
There's more than just 2 diagonals in a 3 by 3 matrix. In a 2 by 2 matrix, there's only 2 diagonals. The one falling from left to right, the one falling from right to left. But in a 3 by 3, do y'all see the pattern? Let's see, I'll use pink. You always start in the upper left-hand corner.
With the
A
first
times E times I, B times F times G. So you multiply down the first diagonal. Then you multiply down the second diagonal. C times D times H. There's the third diagonal. Now your position still at the C. You've gone all 3 diagonals. So now you start at C and you go in the opposite direction. C times E times G. A times F times H. And B times D times I.
Y'all see the pattern?
3 diagonals falling from left to right minus 3 diagonals falling from right to left.
Well, if that doesn't make it clear, then I don't know what does. What would my mother say if she were here? Clear as mud. Clear as mud. Let's do one with numbers.
It's not nearly as bad as it might look.
What was this?
You didn't type in the answer? 26.
Oh, okay. Now we'll go. Okay, not nearly as bad as it looks.
Okay, this is number 11. Okay, so here we go. We have our big absolute value bar. 3, -5, 2, and 1, 3, 6, and 2, 1, -6. I rewrite the first 2 columns. Now, I better make sure I don't miscopy this.
Oh.
Because if I miscopy even one little number or drop a minus sign accidentally, I can assure you my answer would be wrong, and so would yours.
And
okay.
That's why anytime you've ever asked, show me something, and said, oh, I messed up, what did I do wrong? And I'm always, let's look at the problem first. That's the number one reason for mistakes, miscopying.
So we've recopied the first 2 columns. 3, -5, 2. I wrote the first column. Now the second column, 1, 3, 6. I have parentheses, minus, parentheses. And now we're going to start multiplying. You start at the first number in the matrix. 3 times 3 times -6. 9 times -6, that's a -54. The next one, 1 times 1 times 1 times 2. What's that going to give me? +2. And then 2 times -5 times 6. -60. Now we go in the opposite direction. We're going to go in the opposite direction. We're still at this 2. 2 times 3 times 2 gives me 12. 3 times 1 times 6. 3 times 1 times 6 gives me 18. Okay. 1 times -5, and that's a -6. It's hard to see. I accidentally covered over that negative, but it's a 1 times -5 times -6. That's going to give me a, and it's a positive. There's negative times a negative. The negative on the 5 and the negative. Now I'm not mistaken. That wasn't just a scribble, was it? Yeah, it's a -6. So that'll be a positive 30. What I do is I work inside the parentheses. I don't start distributing minus signs. I go -54 plus 2, that's a -52. -52 minus 60, is that a -112? So these here, I'm getting a -112. A -52 minus 60 gives me a -112. I have this pink minus, that's from the formula. Now let's do this one. We have 12 plus 18 plus 30. 12 plus 18 is 30. Plus 30, oh, that works out pretty nicely. What am I getting? 60. -112 minus 60 gives me a -172 for my final answer. Any questions there?
So these matrices, we're assigning a number for every square matrix. negative 172.
Mm-hmm.
Okay.
Any questions there?
It's a mess. Okay.
You know, actually, I'm looking at it thinking, wow, that's pretty neat. I mean, neatly written, for me at least.
Yeah.
3 diagonals falling from left to right minus 3 diagonals falling from right to left.
Make sure you do the ones going.
You start at the first number. That's the first product you get. The one when you start at the first number.
If you start doing the...
If you go the opposite direction, you're going to get it wrong by a sign. If you went the wrong way, you would have a positive 172 rather than a negative 172.
I like this. Number 12, I like them when there's a lot of zeros. Well, at least there's
I
zeros.
should have asked him, what number is think about how we're multiplying these things. What number should you hope you have a lot of? 0. Because if you have a 0 in a diagonal, that means the whole product's going to be 0. So whenever I'm looking at these things, I'm always hoping there's a lot of zeros. Negative 2, 8, and 10. 3, 4, negative 4. And 6, 0, 0. And what will I do first? What am I going to do before I do anything else? Before I start multiplying, I have to do something. No, I don't have to. I see it fine in my head. The rest of y'all, I think y'all like to see. Do y'all see what's happening if you don't recopy? You're wrapping around. 3, 3, negative 6. Then 1, 1, go back to the 2. You're at the 2. Wrap around to the negative 5, 6.
The first time we ever saw it, the teacher did wraparound. I remember I was tutoring a student, and their teacher was doing it. This was years later, recopying the first 2 columns.
Shepard,
and I
recopying. I was like, why did anyone show that to us?
That would have been easier than wrapping around.
Okay, recopy the first 2 columns. 3, 4, negative 4. And then I have my big parentheses minus big parentheses. We start at the negative 2. Negative 2 times 4 times 0 gives me 0. That's why I like the zeros. 3 times 0 times 10. Another 0. So 0 plus 0. 6 times 8 times negative 4. 6 times 8 times negative 4. That's 6 times 8 is 48. 48 times 2 is 96. Times 2 is it 216? No, that's no.
What is it, 192?
Okay. Negative 192. And be careful, I've covered over this minus. There. Now we go in the opposite direction. Okay, we're going to go in the opposite direction. 6 times 4 times 10 gives me 240. Negative 2 times 0 times negative 4 gives me 3 times 8 times 0, another 0. Let me ask you something. What do you think the determinant would be if you had an entire row of zeros or an entire column of zeros? If that 6 right there had been a 0, what would the determinant be?
Would I have the 240?
It wouldn't have the 240. You wouldn't have the 192. I think you'd have 0 minus 0, which is 0. So if you have a row that's nothing but zeros, or a column that's nothing but zeros, your determinant is going to turn out to just be 0. Well, let's see. This first set of parentheses, that's a negative 192 minus that second set of parentheses is a 240. 192 minus 240, is that going to be a 432? Someone check me there. Negative 4, yes, 432. Mm-hmm. for my final answer.
It seems like we've gotten a long way off from
Solving systems of equations. That's where we're going to pick up on Wednesday. We can use determinants to solve systems. Oh, what did you do? Type in the answer. Negative 432. We can use determinants to solve systems of equations. So there's been a point to all this determinant stuff. It's called Kramer's rule. We're going to pick up here the next time. We'll see a new method, something other than elimination or substitution. We're going to see Kramer's rule, how to use determinants to solve systems of equations, and we have some word problems. So that's what we'll be doing on Wednesday.
So we're going to end the semester doing some word problems.
Okay.
Wow.
Any questions there?
What the heck?
Okay.
So cute.
Okay, stop recording.
Oh, okay, I'm going to stop recording.